All right, so the next page of notes is about checking the validity conditions. So if we look at the way the regression equation is written, so here it's written in terms of the betas, so these are the population values. Basically, you have the assumption that the betas are fixed, right? That you have one population intercept and one population slope, and that the only thing that varies is the residuals. So the idea is that there is some true population regression line, and that the errors are varying randomly around that regression line, right? That the data points have this spread. So we're actually making assumptions about how those residuals are distributed. So we're assuming that they're distributed normally around the regression line, that they have a mean of 0, so you don't have more data points above the line than below the line, and that there's a set variance, right? That you have the same variance whether you're low on the scale or high on the scale. So those are our assumptions, and they're actually connected to the assumptions that we made in previous chapters when we were talking about ANOVA. Okay, so the first one is new, that the association between y and x should be linear in the population. So that makes sense since we're doing linear regression. So obviously you can just look at this in the scatter plot, but I want to show you another way to assess this, which is using a residual plot. So in this plot right here, I have the residuals on the y-axis, and then the explanatory variable is here on the x-axis. Okay, so basically we want to see that there's just this random pattern of points, the residuals around the x-axis. So you can sort of imagine that if you took this regression line and you shifted it down, right? So sort of imagine like pulling that line down so that it was flat. That's what the residual plot is showing you. Okay, so we have our residual plot here, and if you just have a random cloud of points around 0, that's good. That would indicate that you have a linear relationship. What we don't want to see is something like this, some kind of curved pattern. That would be a violation of the conditions because this would indicate a non-linear relationship. So I'm looking here at the residuals versus fitted graph. So this one is a little bit easier to make in R, and I'll show you how to do that in a later video. So here, this one's a little bit different because it has the residuals on the y-axis and the fitted values, that's what R calls y hat. So the predicted values here on the x-axis. But you read it the same way. So when I look at this plot, I don't really see any curved pattern here. And if you have no curved pattern, then that's an indication that you have a fairly linear relationship. Okay, so that one should be fine. The second one is the same as what we've seen in previous chapters, that the observations need to be independent of each other. And that's going to be based on the study design. That's not something that we necessarily check with graphs. So there's ways that this can be violated, so things in the design to be looking for. It may be violated if the data were paired or grouped somehow. So this is something we had talked about before. If they were paired or grouped, then those aren't really independent observations. Or another way that we can get observations that aren't independent is with a time series. So, or if you have a time series. So this would be like a scatter plot where you have time on the x-axis. And this is just potentially a problem because sometimes you have two time points and they're actually correlated with each other, right? You don't really want to think of them as independent observations. Okay, the third is that the spread of the residuals doesn't depend on the explanatory variable. So we've seen that before and thought about it in terms of the spread being the same in each of the groups, but there aren't any groups here. Now we just have a continuous explanatory variable. And again, we can check it using the residual plot, but we're looking for different things here. Okay, so what we want to see is we want the variability around the line to be about the same no matter where you are on the x-axis. So this one would indicate constant variance. Constant meaning no matter where you are on the x-axis, the variability is about the same, right? The vertical spread here is about the same. Okay, what we don't want to see is the vertical spread being small in some places and really large in other places. So sometimes people describe this as like a funnel shape or a fan shape, like it fans out. This shape would indicate non-constant variance. Okay, so looking at the plot for BMI and cholesterol, I really don't see anything like that. I don't see that funnel shape. So if I don't have that funnel shape, it's safe to assume that we have constant variance here. Okay, so that looks pretty good. And then another new type of plot is useful for deciding if the residuals are normally distributed. So this is called a QQ plot or a quantile plot. There's a couple of names for it. I'm not going to go into the details of exactly what this shows, but basically you're comparing the residuals that you actually have to the residuals you would get if it were really normally distributed, right? If it were perfectly normal. So what we want to see when we look at a QQ plot is we want to see a straight line, right? Because that would indicate that the residuals look just like we would expect if it were really normally distributed. If we see sort of a curve around the line like this can indicate skew. So like this one where it dips below in the middle, that would indicate right skew. Something like this where we have an S shape, this would be when you have the wrong weight in the tails. So maybe too many extreme values or not as many extreme values as you would expect. So I'm not going to require you to know the details of this, but I just wanted to point out that different kinds of violations can produce different shapes. Okay, so when I'm looking at this one, I mean, it is a little bit curved. You might think that there's a little bit of skew here. So I would say that some curve which may indicate non-normality. So another thing to remember is that normality is going to be affected in some cases, or at least the assumption is more or less important depending on the sample size. We do have a nice large sample size here. And so when you have a large sample size, that probably is going to help you out with inference. So F or T would probably be, whoops, okay here. All right, so this is going back to the house prices data. And I showed this one in jump output actually, just so you can see that it looks a little bit different. I also wanted to use jump output because notice this is a residual by X plot. So it actually is using the explanatory variable on the x-axis instead of the predicted values. But you really don't have to worry about that because you read them the same way. All right, so I'll give you a second to pause the video and think about which of any of these validity conditions do you think might be violated. All right, linearity, I'm not really worried about that. I don't notice any like curved pattern or anything like that when I look at the residuals. It looks pretty much symmetric on both sides of 0, so I think linearity is a reasonable assumption. The one that I'm most worried about is constant variance, or the fancy word for that is homoscedasticity. So if we look at it, I'm a little bit afraid there might be a bit of a funnel shape here, right, where it's a little bit more precise estimates down on the low end and less precise on the high end. So that would be the one I'm most worried about. To be honest, it's a little bit hard to tell because it's a pretty small sample size, but that's something I would be concerned with. Normality, it actually looks pretty good. These points are falling nice and close to the line. And jump output actually helps you out by giving you these dotted lines as a guide. So the fact that you don't see anything outside of those dotted lines would indicate that there's no reason to think that this isn't normally distributed. And then independence, we said that's based on design. There's no pairing here, there's no time series, so I think that the independence condition would be fine.